Okay, so just for the sake of completeness on the recording, we're talking about fitting polynomials to data if we extend our compressibility versus pressure data to higher pressure, and using the trend line options on Excel, you can choose either a line, which gives you a straight line fit, or you can choose a polynomial and set the order to get the coefficients of different order polynomials. Okay. Okay, so we've done example number 10 now. We've used a nonlinear regression to obtain the values of B0, B1, and B2. We also did the same for a third order polynomial fit. And now we want to have some way of judging, what's the quality of the fit? What's the goodness of the fit? So one of the parameters that you can use to see how good a fit is to look at what's called the standard deviation of the regression. This is just a extension of what we already looked at before when we looked at a linear fit, for a linear fit at the standard deviation of the residuals. Okay, but in general, this parameter for any parameterized equation that you're trying to fit, it's just equal to the square of the residuals, right? The square of the observed value minus the predicted value by the fit model. And then you take the sum of the square for each data point that you measured, you divide by the degrees of freedom, and then you take the whole thing and you take the square root, right? And that's a standard deviation. That's the sort of characteristic quantity by which each point differs from the fit model. Okay, and in this equation, nu, the degrees of freedom, is equal to n minus p, where p is now the number of fit parameters. So p depends on which fit model you're using, right? So for a linear fit, p would be, of course, 2, right? Because you're fitting a slope and an intercept. But for a quadratic, p would be 3, because you're fitting 3 fit parameters. Okay, so yeah, suppose you do a regression analysis of your data. Let's say you're comparing 2 different models. Model 1 gives you a sigma of 0.0152, and model 2 gives a sigma of 0.00705. So that means that basically the model 2, the fit model is closer to the measured values on average than for model 1. So you could say that model 2 provides a better description of the data than model 1. And so if you increase the number of polynomial terms in a fit, usually the fit is bound to get progressively better, right? If you give the function more flexibility, it has to somehow be able to fit the data better. But this raises the question, at what point is the improvement really statistically significant, and at what point are you just fitting the noise in your data? Okay, and so I'll give you sort of a real life example of that. I'll just show you a little quick example. Okay, so shown here is some data from my own research, where in this particular experiment, I was scanning a high resolution laser, and in order to calibrate the frequency, right, to know what frequency you're at the same time that I was taking an experimental spectrum, I was also taking a reference spectrum of a molecule with known frequencies. And so this plot here is a plot of the point number along the scan versus the wave number of the light in units of reciprocal centimeters. Okay, and the laser that I was using had a problem, which was that the grading basically was not scanning entirely linearly. So if you look at the comparison of the data, which is shown as markers, to the linear fit, which is shown as a straight line here, you can see that there's kind of this wiggling going on. So, these data points are above the line, these ones are below, these ones are above, these ones are below, and so forth. And it's really obvious, it might not be so obvious if you just look at the raw fit, but if you plot the residuals, then this is what they look like, and you really can see that there's this wiggle going on. So it looks like you need more, you would need a high order polynomial in order to really accurately go through all these data points. So I'm using a program now called Igor Pro, which you don't need to learn how to use. It's just a little bit more convenient for this than Excel, just to show you really quick. So I could also fit this to a polynomial of a particular order. Like, let's say I'll try a third order polynomial. Okay, so that actually doesn't really provide all that much improvement. But if I go to a higher order polynomial, like say, I don't know, 10, then you can see that, okay, so it's still not perfect, but the residuals are looking a bit more like they're closer to being randomly distributed about 0. Okay, there's still a little bit of wiggle here and there, but we can see that this fit is clearly better than the previous one. And so maybe you actually want to go a little bit higher. Maybe you want to do like a 15th order polynomial or something like that. Now, at least, in this region, for example, it looks like the residuals are more or less randomly distributed about 0. They're not going up and down again. So maybe this is a statistically significant, or in a statistically appropriate fit to get a proper calibration curve in this particular experiment. Okay, but we are gonna look at some other, so we're gonna stick with our initial example to calculate some statistics. So let me see. Any questions so far? Sorry, share screen. Then I want to go here. Yeah. Okay, so first we're going to use this standard deviation of regression. And so in the next example, we're going to calculate the standard deviation of regression for fits of the compressibility data using a linear equation and a second order polynomial. Okay, and we'll go ahead and do the third order polynomial as well. Okay, and we're going to use these values to show that the second order polynomial provides a better fit to the data than the linear equation. Okay, so I'm going to show you how you can do that pretty simply using an Excel spreadsheet. Okay, and we're just going to use this formula that we talked about. So I'm going to exit this program and find my Excel spreadsheet. And you can find this Excel spreadsheet, of course, on the Blackboard with all the numbers filled in. Okay, so how do we calculate the standard deviation of the regression? Well, first we need to calculate the fitted data points so that we can calculate the residuals. And how do you do that? Well, you just use the equation, the fit equation. So for the first order polynomial fit, it's just the equation of a line. So we want to calculate the intercept for this particular fit plus the fitted slope. And I'm going to put $signs here so that I can copy this formula later, times the X value. Okay. And so for the second order fit, it's going to be the same thing, but we just take the intercept plus the linear coefficient times the X value, plus we need a third term now, the quadratic term. So the quadratic coefficient times the square of the X value. So I'm going to raise this to the power of 2. Okay. And then if I drag this formula down, then I get points corresponding to this fit. And we'll do the same thing for the third order, but I'm going to save a little bit of time by just copying over this equation. And then the one trick you can do is just drag over the cell references. Okay, so now I got the quadratic, but I need one more term. I need to add one more term to get a third order fit. So I'm gonna add the third order polynomial coefficient times the cube of the x value. Okay, and hopefully I did this all correctly. Looks like, oh, here's a mistake. Something's wrong. What did I do? Yeah, wait, which one? This one. F2, where is that? Ah, okay, that should be B2 because it's a linear. Okay, let me just make sure that these other equations are correct. Yeah, this one looks correct. This one, I think now it's, oh. Okay, now maybe it's correct. Sorry about that. Okay, yeah, now these numbers look like they're matching the experimental numbers a bit better. Okay, so that looks correct to me. Okay, so now for each data point, we're going to calculate the square of the residual. And so the definition of a residual is just the measured value, so the measured z value minus the calculated z value for a particular model. And then in this case, we want the square of that. So I'm just going to put parentheses here and square it. Oops. Sorry, I'm missing a value of 2. Okay, now it works. And I can copy down this formula. I'll just make sure that it looks correct. Yep. I'm going to do the same thing for these other two fit models. So I'm going to take the observed minus the calculated and take the square. Okay, and for the third order fit, I'm going to do the same thing. Observed minus calculated. Squared. Okay, so in the formula, when you calculate the standard deviation for the regression, you want to take the sum of the square of the residuals. So we're going to sum up all the numbers in this column. And then you divided that number by the degrees of freedom, which for the linear model is 6 minus the number of parameters, which is 2. So 6 minus 2 is 4. So I'm going to take this guy divided by this guy. And then the standard deviation of the residual is just the square root of this value. And this value, before you take the square root, is called the reduced chi-squared. Okay, and so I can just copy this formula over. I believe that should work. So I can calculate the same thing, sum of the residual squared for the second and third order equations. And then I can copy over the formulas to get the reduced chi-squared and the standard deviation of regression for the other two fit models. Okay, and so you should notice that when you increase the number of fit terms, right, from a first order to a second order, the standard deviation of the regression decreases quite a bit. So we could just calculate really quickly, you know, what's the ratio of the standard deviation for the linear fit versus the quadratic fit, and it's about a factor of 2. Okay, and then when we went from the quadratic fit to the cubic fit, the fit got a little bit better, but maybe not so much better. So if you calculate here the ratio of the standard deviations going from the quadratic to the cubic, they only improved by about 15%. Okay. So the question is, is it statistically significant to include a quadratic term and a cubic term, right? So that's what we're going to talk about next. So I'll go back to the presentation. Okay. I think everyone can see this now. Any questions before we continue? Okay, I'll keep going. Okay, so the test that we're going to use for this is called an F test. So this is a statistical test that can be used to determine whether adding another term in a model function is justified at the 95% confidence level. In other words, can you be 95% sure that this term is meaningful, that it's actually significant? Okay, the F test is based on the reduced chi-squared, which is given by this equation here. This is just the square of the equation that we saw on the previous slide for the standard deviation of the regression, right? So the chi-square is just the square of this sigma. And here again, nu is n minus p, where n is the number of measured data points and p is the number of parameters in the fit model. Okay. And okay, so let's say you measured some data. You have two different model functions, y1 of x, y1 of x and y2 of x. And the number of degrees of freedom are nu1 and nu2, respectively. And the number of measurements is the same. You're fitting the same data. And let's say when going from model 1 to model 2, you added 1 degree of freedom, right? You removed 1 degree of freedom by adding 1 fitting parameter, right? So model 2 has 1 additional fitting parameter in addition to the parameters in model 1. Okay, so nu2 is going to have, it's going to be nu1 minus 1. You're going to have 1 less degree of freedom in model 2. Okay, so for example, this could be if you're going from a second order polynomial fit to a third order polynomial fit, and you want to see whether you're justified using a third order polynomial or whether the second order polynomial is good enough. Okay, and so there's this thing in statistics called the F distribution, and the F test is based on this distribution. We're not going to go into the detail of deriving that. We don't have time in this course, but the F parameter, if you change the number of degrees of freedom by 1, then there's this function f of 1 comma nu2, and that is defined like this. So it's the number of degrees of freedom for fit model 1 times the reduced chi-squared for fit model 1 divided by the reduced chi-squared for fit model 2 minus the degrees of freedom in fit model 2. Okay. Okay, so how then do you apply the F test? Well, here are the steps that you would follow. So you're going to use this equation on the previous slide. It's also in your lab, your lab instructions in chapter 1 on your lab manual on equation 48 is what it's labeled. And you're going to use this equation to calculate the observed value of the F function, right? You calculate it just based on the formula. Then you're going to compare the observed value to the limiting value at 95% confidence of the F parameter. And you can get that from the final column of table E1 in your lab manual, which is also shown on the next slide. And if the observed F parameter is greater than the limiting F parameter, then the second model, the model with more fit parameters, is preferred over the first model. But if the observed value of the F parameter is less than the limiting value, then the better fit that's provided by model 2 is not actually statistically significant, and you're not justified in using it. Okay. So here's the table that we're going to use And the limiting 95% values for the F parameter are given in this final column of this table here. This is the column that you want to use. Okay, and so we are going to now do an exercise using the F test to show that the second order polynomial provides a statistically better fit to the compressibility data than the first order polynomial. But we're going to see that the F test is going to show that it's not necessary to use a third order polynomial. Okay, so how do we apply this F test? Well, let's go through the example. I'm going to actually exit out of here. I have a little bit easier time writing on over here. Okay, so basically we're going to, we're doing an F test. Oops, everyone can see this, yes, F test. And we're going to compare the linear fit with a quadratic fit with a cubic fit. Okay, and so the number of fit parameters for each fit for a linear fit, it's 2. You get the slope and the intercept. For a quadratic fit, it's 3. And for a cubic fit, it's 4. So the number of degrees of freedom then for these different cases are, so we had n equals 6 in our particular example, right? We measured 6 data points. So the degrees of freedom is 6 minus the number of fit parameters. So for the linear fit, that's going to be 4. For the quadratic fit, it's 3. And for the cubic fit, it's going to be 2. Okay, and we already calculated the reduced chi-squared in the Excel spreadsheet. So I'm not going to go back over to the Excel spreadsheet. You can check it if you want. You can download it on Blackboard and from Blackboard and look along as we go. But the numbers that we calculated for the linear fit were 1.64 times 10 to the minus 4. For the quadratic fit, it was 4.04 times 10 to the minus 5. And for the cubic fit, it was 3.03 times 10 to the minus 5. Okay, so first, we want to compare the linear fit model to the quadratic one. Okay, so we can call the linear one model 1, and the quadratic one, we could call that model 2. Okay, so how do we make a comparison? Well, first we calculate the value of the F parameter, and the formula that we had was F of 1, comma, the degrees of freedom in the second model, which is nu 2. That is given by nu 1 times the reduced chi-squared for fit model 1 divided by the reduced chi-squared for fit model 2. minus the degrees of freedom for fit model 2. Okay, and so if we plug in the numbers from our example, comparing the linear fit to the quadratic fit, the value of nu2, well, the second fit model here is the quadratic one. So the value of nu2 is here, it's 3. So we're looking at the f1, 3 parameter. And our observed value of f1, 3 is degrees of freedom in fit model 1, that was 4, times chi squared for fit model 1, that's 1.64. Sorry, 1.64 times 10 to the minus 4. And then we're going to divide that by chi squared for model 2. That was 4.04 times 10 to the minus 5. Okay, and then we subtract from this whole thing nu2, which is 3. Okay, and if you plug this into a calculator, you should see that this comes out to 13.2. Okay, so then we need to look up what is the limiting value of f13. We need f13 limiting, and that value, if we go back to the presentation, that was, so nu is 3. So we want this row right here, and so we want this value. So the limiting value of the f parameter is 10.13. Okay. And so f observed is greater than f limiting, which implies that the quadratic fit is statistically significant. Quadratic fit is statistically better than the linear one. Oops. And linear. Okay. And then in the second part of this problem, we're going to do the same thing, but now we're going to compare the cubic or compare quadratic to cubic. Okay, and in this case, we're going to have f of 1, comma, okay, and so in this case, the should be a 2. So in this case, the fit model with the greater number of parameters had 2 degrees of freedom. So we want f of 1, 2. And so that is going to equal the degrees of freedom for the first fit model, so the quadratic one. Well, that's 3 in this case, times chi squared for the quadratic model. That was 4.04 times 10 to the minus 5. It's this number here. And we divide by chi squared for the second model that we're comparing with greater number of fit parameters. That's going to be 3.03. Oops. Times 10 to the minus 5. And then we subtract degrees of freedom of the second model, which was 2. Okay, and now if you calculate this, you should get exactly 2.00. Okay, so we could call this F12 observed. And what is F12 limiting? Is it going to be the same number that we used last time? No, because the number of degrees of freedom is different now, right? So we have to go back to our table. We have to look up this limiting F value for 2 degrees of freedom. So that's in this row here, and the value is 18.5. Okay. So is the observed value of F greater than the limiting value? No, it's not even close. So in this case, we would say that we are not entitled to include a cubic term in our fit, right? It is statistically does not provide a better fit. Okay, does this make sense? Any questions? Oops, sorry, wrong window. Okay, so that's actually all of the material that we needed to cover for today. That covers all the rest of the statistical analysis. We'll meet one more time and we'll talk a little bit about the expectations for writing lab reports. And I'll give a little bit of advice on that. And then the following week, you start your laboratory exercises. So just a reminder, if you have not yet done so, please do remember to go ahead and take the safety quiz on Blackboard. I believe your deadline for getting that done is tomorrow at midnight. And you can't get access to the lab manual and to the pre-lab problem sets and whatnot until you have completed the safety quiz. So please go ahead and do that. And then you can take a look at the pre-lab problem set, pre-lab video for your lab next week. Go ahead and answer the questions because you need to bring those with you to lab. And also make sure you have to bring with you to lab your personal protective equipment. That includes a lab coat and lab goggles. And you also are going to need your lab notebook. I believe that's everything that you have to take with you. Any questions about that? Okay, if there's not any questions, we'll finish a little bit early today. And have a nice evening, everyone.